Thank you, Jose Luis. As he says, I'm working now with Geosciences Barcelona. I joined in January, and I'll be working with Jose Luis to hopefully deliver some interesting outputs from this project. And as we were discussing before the presentation started, 2 years or maybe 3 or more isn't a great deal of time in research to create something new and exciting. But as you can see from this opening slide, we do have a lot of partners in academia and in industry. So we hope that, as we say in English, many hands make light work, and we can give some interesting results. And we do have a bit of a running start with this project because it was born out of a UK research project called the GEO project, which stands for Greenhouse Gas Removal by Enhanced Weathering. And hopefully throughout this talk, I'll explain what all these words mean, such as enhanced weathering and mine tailings, if you were unaware. So this is who we are then. This is the Details project. We're funded through the EU Horizon 2020 scheme, essentially from the start of 2022 till the start of 2024. Jose Luis is partnering and supervising on this project. And we started to make some connections with collaborators at the University of Alicante, such as David Benavente from their petrology group, who was helping us with characterizing our samples. And we're making plans for future experiments in microbiological applications with Professor Phyllis Lamb at the University of Southampton. And I'll explain where the microbiology comes into this a little bit later as well. So here's our justification for our project. We're hoping to contribute to the necessary reductions in atmospheric CO2. As we're all aware, these have been projected to keep rising over the next century based on several IPCC CO2 emission and temperature pathways and different scenarios. Consensus, at least as defined by the Paris Agreement, is that if we're going to limit our warming to well below 2 degrees Celsius or 1.5 degrees over the next century, we need to reduce our CO2 outputs. But we also need to start taking CO2 out of the atmosphere. So we need to start doing CO2 removal on a scale of tens of gigatons, which is obviously a huge challenge for us as a society. And the time to act is now, or even before now, but we're in this position, we are where we are. Looking specifically at the mining industry and their contributions and their role in this undertaking, it is a big emitter of CO2. It's not the biggest compared to fossil fuel emitters such as steel production and oil and gas, but it is still a significant emitter. And one of the big, we could call it a problem or maybe a necessary evil or however we want to call this, the mining industry isn't going to stop, and we can't allow it to stop. If we want to mine for our raw materials, for our low carbon technologies such as solar panels and other renewables, we still need the materials. So the expression is that if it's not grown, it's mined. So that's going to continue into the future as a consequence. And whether that becomes a problem through larger emissions depends on how the industry moves forward. But the emissions that they are producing, the industry is definitely aware of these. So they are now trying to make steps to improve their CO2 emissions down to either neutral or even possibly negative emissions. So that comes with improving production efficiency, implementing renewables, important reduction efforts that are being made. So one of the key problems or one of the key issues that the industry has is all the waste materials that it's currently sitting on. And what it might be sitting on is one of the largest untapped sources for CO2 removal. That's millions of tons of mine waste produced annually, or that already exists in historic tailings piles. So to briefly explain what I mean by geochemical CO2 removal, we're basically looking at ways to speed up the natural process where the Earth governs its carbon balance through rock weathering and CO2 uptake by the ocean and by carbonate mineral precipitation. So rocks will naturally react with weakly acidic rainwater in the atmosphere, which over time releases elements from the minerals that are contained in the rocks. That's what we call mineral dissolution. In the case of rocks which contain divalent cations, such as magnesium and calcium, these elements are released from their mineral structure with a reaction with atmospheric CO2 and water. When the elements are released from their mineral structure, they'll react with the CO2 and the water to form stable bicarbonate solutions of magnesium or calcium. This is what we call alkalinity. And when we do that, the CO2 that was once in the atmosphere is therefore taken out of the atmosphere and effectively stored as alkalinity. It's now a safe storage of the CO2. These alkalinity products eventually end up in the ocean, where it might go via rivers or groundwater, but inevitably this is where the alkalinity ends up, and it can reside there as alkalinity for hundreds of thousands of years, or it will eventually precipitate as carbonate minerals. Now, when we think about these geochemical CDR approaches, CDR being CO2 removal, the natural process, which we're looking at here, is a slow one. It takes hundreds of thousands of years to occur. So in the space of a year, the Earth will maybe naturally take up 1.1 gigaton of CO2. And as I've already explained, we might be looking at the necessity for tens of gigatons of CO2. So that amount that we are requiring, on top of the amount that we're also emitting from fossil fuels, that dwarfs the amount that we're able to take up naturally. So one of the key methods that we need to take to achieve some of these high targets is to speed up the weathering reaction in what's known as enhanced weathering. So again, here we see our natural chemical, geochemical removal of CO2. We have our weathering, which produces bicarbonates, which are stabilized by magnesium and calcium. And then they're stored as either alkalinity or they precipitate out as carbonates. Enhanced weathering essentially follows the same general trend, but each of these steps is deliberately accelerated. So the most obvious example of a way to accelerate the weathering is to crush up the material. And this doesn't just go for rocks. If you think of an Alka-Seltzer or a hangover tablet or a vitamin tablet or even a stock cube, if you put it in water, if you crush it up, it'll dissolve quicker when it's broken up and stirred. And that's because you've created a more reactive surface area. You've got a higher surface area to speed up dissolution. So the same is true for rocks and minerals. But there are several other ways of achieving enhanced weathering. Some of the ones that could be applied to speed up dissolution rates of minerals include spreading our material, so our rocks or our minerals, over large surface areas, such as a field. We can add heat, we can use more water, we can use acids, we can increase the CO2 concentration, which, like acids, will create an acidic environment to speed up dissolution reactions. Or we can use microbes and microbial processes to alter the environment. Equally, the same is true for changing our bicarbonate solution to a precipitated carbonate mineral. We can increase precipitation rates through creating an alkaline environment, reducing water content, changes to CO2, temperature, or different microbes that may promote alkaline conditions and therefore create an environment that favors carbonate precipitation. But the overall purpose of this, of enhanced weathering, is to achieve mineral dissolution, alkalinity production, and possibly carbonate precipitation on a scale of tens of years rather than thousands of years or longer. So one of our first considerations when we're looking to implement geochemical CO2 removal processes and approaches is, what are the materials that can be used? What are the best materials? So our best options for CO2 removal by enhanced weathering or by mineral carbonation are from silicate-hosted ultramafic and mafic rocks, such as basalt, as we see here. And that's because they're full of magnesium-rich minerals, such as olivine, as well as some other magnesium and calcium-rich minerals. So as we all know, basalt is produced by volcanic activity, but chemically and mineralogically similar rocks that cool and solidify within the Earth's crust are also equally suitable. So our plutonic or intrusive rocks, such as gabbros and periddotites. We do actually see real-life evidence of weathering and carbonation in some field examples, such as these serpentine-rich periddotites from Oman. So we see this without even having to implement enhanced weathering. This is just the natural reaction happening before our eyes. And for this reason, these rocks are being investigated for their CO2 removal strategy possibilities. So places like here in Oman, also the Carbfix project in Iceland and parts of the United States. These are big areas for where these investigations are going on. And one of the biggest issues we face, though, is the ability, or possibly lack of ability, to react our CO2-rich fluids or our atmospheric CO2 with as much rock as possible. We're trying to use just more than what we see here, for example, which is the surface exposure for these reactions to take place. And as I mentioned in the previous slide, crushing and grinding the rocks is an obvious solution to this. The issue with that, of course, is that crushing and grinding rocks is costly in terms of financial penalties, but it's also energy intensive as well. And if we're going to crush and grind a rock up, we might even be using emissions or creating emissions and using fossil fuels and creating CO2. So it's not always the easiest route to follow. But at the same time, it's a necessity. It's a necessary step for speeding up the reaction. We increase the surface area, the reactive surface area of our rock. We increase the mineral kinetics. So one of our enhanced weathering methods is to take a rock, crush it up to finer particles to speed up the reaction with CO2 and water. But is there a way to achieve this enhanced weathering step without enduring these financial and energy intensive penalties? Is there a way around having to take a rock out the ground and just crush it up purely for the purpose of CO2 removal? Well, if we look around us, the mining industry, particularly mining for metals and precious stones such as diamonds, requires the crushing and grinding of materials in order to extract the commodities. The mine sites will produce what are commonly known as mine tailings as one of its waste outputs. And tailings are the commercially uneconomic material that remains once we've separated our commodity, such as diamonds or copper or gold, following chemical and mechanical processing. So we're separating out the economic stuff from the uneconomic stuff, which is predominantly silicate minerals. And those silicate minerals have then been ground down to clay, silt, or sand-sized particles and stored in dams and ponds, such as the one we see here. Mine sites do produce other waste materials as well on site, such as overburden rock. So that's the overlying bedrock that we need to remove to get to the economic ore deposit. And normally that's just bulldozed or exploded, or we just have to get that out of the way to get to the stuff that we want. So that's stored on mine sites as piles of blocks and rocks of various sizes. The other common material is slag material, and that's formed a bit further down the process chain, normally at a smelter plant. And that's where we further treat our ore concentrate with heat, and we create a glassy byproduct as a result. But we're going to focus on mine tailings, at least for the details project, because these are the most abundant rock waste produced in this optimal way of fine grain sizes for CO2 removal purposes. And as well as that, there are several other benefits of using tailings over natural rocks or even different mine wastes. Firstly, there's a lot of it. Tens of gigatons are produced annually, which is a lot more than slag material, for example. And as I said earlier, this will continue to grow with different targets for mining in the future, for our electrical and renewable resources. And this is going to be a global distribution as well. Mines are distributed all over the world, so there's no real geographic restrictions to where mine tailings occur. As I mentioned, perhaps the major benefit of this is that we have these naturally man-made fine grain sizes, less than 200 microns typically, already ground down to this fine grain size. So this is already happening as part of a conventional mining process. We don't need to add additional energy requirements to achieve these favorable grain sizes. It's already being done. Another advantage is that the mining industry is well equipped and knows how to move around high tonnages of these rocks and powdered materials on what is essentially a 24/7, 365-day continuous conveyor belt system. So the infrastructure is in place to move high tonnage rocks and water around for any reaction system that could be implemented, particularly as a lot of mines work with wastewater treatment plants, which could be harnessed for their reaction possibilities. There's also sufficient expertise within the industry. A lot of mine companies have very good geoscientists, biologists, engineers, and so on. And of course, if you've ever been to a big mine site, they're usually very big, and there's a lot of space on the land available for any implementation purposes. So the first point there about the high tonnages, some of these high tonnages that are produced are the exact right kind of chemistry and mineralogy for CO2 removal purposes. Many metals and precious stones come from these magnesium and calcium-rich silicate rocks, which are already important targets for geochemical CO2 removal strategies. And the industry interest is now there too. So big companies like Anglo American, De Beers, Rio Tinto, and others are all now showing interest in how they can use their tailings for CO2 removal purposes, which is obviously good for people like myself because it means more funding for work and projects. But for them, it's because they want to do something about the several gigatons of CO2 that they are emitting each year through their extraction operations. So basically with mine tailings, there's a lot of it. There's a high chemical potential for some of it. There's expertise, there's resources, but there is still a lack of knowledge about CO2 removal strategies with mine tailings. The main questions being just how much potential exists, what are the main targetable types of tailings, and how do we efficiently and effectively realize the overall potential that is out there. And to answer that first question about how much potential really exists, we have conducted a couple of studies to determine both the overall maximum potential of the industry. So that is basically every possible mine site, whether it's potentially favorable or not, what is the maximum CO2 removal potential of that material. And where that study gives us a very ambitious or positive target of up to 4.5 gigatons removal of CO2 each year, it's maybe not a realistic number because some of those mine sites just they don't contain the rocks that react well with CO2. Even if they contain magnesium and calcium-rich minerals, some of that potential is essentially locked up in minerals that just react too slowly to be realistically effective. So by focusing on a set of minerals and a specific set of tailings types that could be effective based on its kinetics as well as its chemistry, we could still potentially be removing up to 0.5 gigaton of CO2 per year. So tailings, they come in a variety of different flavors. They come in different variety of compositions, basically with different ingredients. Some are better than others for removing CO2. In other words, a tailings material that comes from an original rock that's full of ingredients like silica and sulfur, they won't be good for reactions with CO2 and water. They just don't contain either the cations that we need, or they just don't contain enough, or they react too slowly. So when we look at gold mines, for example, or iron mine tailings, they're not necessarily going to be suitable for CO2 removal strategies, at least in this way. However, commodities such as platinum and platinum group metals, diamonds, nickel, talc, and asbestos, these come from our mafic and ultramafic rocks. So they contain more magnesium and calcium. And the tailings are basically a reflection of those original compositions. So these are the best tailings for CO2 reactions. Olivine, which is one of our champion minerals, let's call it, because it's quite fast reacting and it contains a lot of magnesium. Olivine can be mined in itself as a commodity. So these tailings are very suitable as well. The annual production estimates vary across these chemically favorable tailings types, from relatively low global production tonnages of less than 1 million tons per year for asbestos, right up to maybe even up to 2 gigatons of platinum tailing produced per year. So while asbestos production is low, that's because it's banned in a lot of countries. Historically, it has been mined all over the world, so there are plenty of historic tailings in countries that have now banned asbestos mining, such as Canada, for example. So we surmise that there are at least 30 countries that host significant tonnages of suitable tailings, in particular South Africa, also Canada and Russia as well. If we weather these tailings and produce alkalinity, for all of those suitable tailings that are produced annually, we can remove up to 0.5 gigaton of CO2 per year. And that's averaged over a period between 2030 and 2100, giving us a total of around 33 gigatons of CO2 removal on that time scale. So that's alkalinity production. If we precipitate out that alkalinity for carbonate storage and carbonate mineral precipitation, we do give a bit of that CO2 back to the atmosphere in that process. So the capacity is effectively halved in that regard, although producing a solid waste material might be a more practical route for the mining industry compared to producing gallons and gallons of solutions which then are released into rivers and oceans. So there's a lot of potential for materials such as platinum group metal tailings, PGM tailings, not because they're necessarily the most chemically suitable, but because there's a lot more produced annually in terms of tailing tonnages compared to other suitable types, such as our asbestos and our olivine, for example. One thing that should be considered is, although we don't include them on our list here, there is some possible suitability for mine tailings such as copper mines, maybe titanium, even iron to some extent. There's minor potential in there. So if we can unlock that minor potential, due to the massive tonnages available, there is extra CO2 removal potential that could be obtained from looking at these mines. So the potential is there, but how do we realize it? Well, we've narrowed it down to a range of possible tailings types to use for the most suitable or the most likely to work based on their mineralogy and their geochemistry, but also, as I mentioned earlier, their kinetics, and by which I mean how fast are the minerals likely to react. Timescales, though, are still too long to be effective, but there are methods that can be utilized to speed up those slow dissolution rates, which we're going to test during the details project. And one that I'll discuss momentarily is microbiological approaches. And our aim in the project is to test samples that are as close to as possible to tailings as they're found at the mine site. That way, these fit into a strategy that can be operated within a mine site as effectively as possible. It would be easier to just take out minerals that work because we know they work and test them in the lab, but that's not going to be much use if we want to achieve gigaton scale removal. So this is one real-life example of some ongoing work from the G Group project that I was working on samples from a large platinum mine in South Africa. So the site we visited is in Limpopo province, about 3 hours north of Johannesburg. It's just one of many platinum sites in that part of the world in the Bushveld complex, which is by far the biggest producer of platinum group metals in the world. And the industry in South Africa wants to explore these opportunities to offset some or all of their CO2 outputs. We know that there are millions of tons of tailings, both in existing tailings ponds and being produced every year. And we know from the desktop study, which I just presented, that there is good potential for the minerals which are contained within these platinum group mineral metal tailings for the right reactions with CO2. So far we've undertaken fieldwork and sampling, and we've characterized the different sample wastes that we've collected in terms of their physical, chemical, and mineralogical properties. And we've also done some initial benchtop experiments with CO2 and water to test the reactivity of these tailings. And so far the results are promising, minus the need to explore ways to speed up the reactions and also to upscale them. So these are the general rock waste that we encountered and we would expect to encounter on similar metal producing mine sites. I already mentioned what these are, so there's a lot of overburden rock that needs to be moved, and that's one of the bigger mine wastes produced. They're usually piled up on site and don't get processed. Of course, there are tailings, which do undergo processing to these fine grain sizes. And the other one that I mentioned is these glassy slag materials, yet more silicate wastes produced further down the chain of refining for the concentrate. So these are then crushed to these granular, angular, glassy wastes. They're a couple of millimeters in length, so they are a bit coarser than our mine tailings. This is our initial bench setup for CO2 reactivities. We basically have a number of 1 litre bottles that contain millicue water and the waste sample. With a CO2 line feeding into the water, we have magnetic stirrers to keep everything in motion, and we have various ports for measuring pH, for taking samples. We ran these experiments over several days, essentially until the pH level leveled out. So our initial results suggest that pH and alkalinity in the solution show a sharp upshoot in the first few hours of the experiment, before generally leveling off and remaining constant for several days, at which point the experiment was stopped. We saw that the fine grain tailings and the fine slags showed the highest reaction rates, the highest cation release, so that's the release of calcium, magnesium, and also silicon. We need to break down that silicon to get to our calcium and magnesium in some cases. And there were notably higher calcium contents in the fluid for bottles associated with tailings compared to the slags. And that's simply because there was more calcium in the tailings than there is in the slags. And conversely, we saw higher magnesium release in the slags because the slags contained more magnesium. We also saw that samples almost exclusively showed a post-experimental increase in surface area or reduction in grain size during the experiment. The average reduction in grain size was around 51% to maybe even 90%. This could be a physical manifestation of the experiment where the materials grinding against each other, or it could be a result of some mineral dissolution which is occurring. And that's why we see the increases in our calcium and magnesium in fluid. So some preliminary conclusions from that particular experiment. The order of fastest reactivity of our targeted waste products was fine slags and tailings, followed by our coarser material, and then our overburden samples. Slags showed the fastest release of magnesium, where the tailings showed the fastest release of calcium and the highest release. And those are reflections of the starting compositions. The dissolution rate showed a steady decline after the first few hours of samples. And as expected, the finer grain sizes showed the highest dissolution rates of chemically similar samples. So we had a fast rate which leveled out. Finer material was the fastest dissolution. And another thing is that these rates that we achieved, they were very comparable at least to other studies that have been conducted on gabbros and basalts and serpentine-rich rocks. The kind of rocks that are known for their CO2 removal potential. So the materials are right in there with the materials that are already considered suitable. So that's good news as well. And what we're seeing is there is potential for these CO2 tailings reactions, at least with PGM materials. But once again, the reactions are still quite slow, especially after the first few hours once we've lost maybe the most reactive minerals or the most fine grain materials. So we still need to find a bit of encouragement to get the magnesium and calcium out of these minerals. They might be trapped in the silica structure, for example, or they just react far too slowly to make a big difference on human timescales. We're talking tens of years is what we want to achieve rather than thousands of years. And what we learned from this study is that there is suitable and abundant tailings out there for large-scale global removal strategies, but we need a global shift as well, a massive shift in the industry, which could create jobs and a different working sector, but we need to do it to achieve the high potential that exists. We still need to better understand these suitable materials, but also the less suitable materials to improve our knowledge and the capabilities of approaching CO2 removal through enhanced weathering of mine wastes. These are the kind of things, these last two especially, are what we want to achieve in the details project. The other one being, we want to speed up these reactions again. So to start with the details project, we want to investigate a range of different tailings types, ranging from samples that we consider we have a relatively high confidence that they will react with CO2, such as olivine dunite tailings. This is a particular example from a mine in Galicia, which we received from our partners at Pasek Minerales. The samples that have received very little attention so far, at least in academic circles, due to their generally unfavorable chemistry, such as the Rio Tinto copper mine in Andalusia, where there might be a bit of calcium and magnesium knocking around, but they're not one of the champion materials, at least. We also have acquired a bunch of other samples to test, including some that we know should have some promise, like kimberlites, which are the rocks where we find diamonds, to some that may have some potential, such as red muds and boron samples, right down again to these lesser understood copper and ilmenite deposits and those from processing activities. So we currently have around 16 samples to test across this reactivity spectrum that we're testing under benchtop reactions with CO2 and water, from our promising to our more unknown to our more unfancied, or perhaps more diplomatically, more ambitious materials. And we've spent the first few months of the project characterizing these different tailing samples by various means such as XRD, ICP, grain size distribution, surface area characterization, so we can understand what materials look like before we subject them to CO2 and water. And we'll look to start our experiments in the upcoming weeks. So hopefully the next time I speak to you or at a conference, we'll have some exciting results to show on that front. In the meantime, we want to better understand our most reactive and our least reactive materials. And we want to finally explore what we can do to unlock the magnesium and the calcium to realize this overall high potential that these mine wastes have. So we know that increasing temperature can speed up batch reactions, so any heat produced at site could be harnessed, or we could conduct work in hotter climates. And we should bear that in mind about where we target these initial investigations. These can speed up reactions. There may also be a case for utilizing high CO2, for instance, harnessing any CO2-rich gases that are typically released to the atmosphere from maybe steel-making plants or anything similar, or incorporating any kind of hybrid enhanced weathering direct air capture scheme. And the benefit of having that high CO2 is the same benefit that we see here using acids and organic or inorganic additives, which can speed up mineral dissolution rates and increase mineral dissolution. Obviously, the management of acids would need more careful consideration for the environment, though. And of course, as I mentioned as well, we can increase surface area exposure to the atmosphere by spreading these materials across fields, coasts, or, we can get a bit creative with this. Can we spread them in greenhouses? Can we spread them on vineyards? Anything like that, where we can put it across land and allow weathering to happen naturally, but perhaps at faster rates. So those ideas are all good in principle and across the subject as a whole, but maybe from the mining industry, they're not the most practical approaches. Heat and CO2 could be harnessed, but not without significant costs and possibly even emission production. And as I said, acids, they can be expensive and they can be dangerous to the environment. Spreading, which we saw here, is one of the more viable options. Mine sites do have a lot of land, but there are still questions regarding feasibility and external environmental influences and how exactly you monitor and control what is happening across a field. So perhaps one viable option is to utilize microbes. And that's the work that we're undertaking as part of the Details project. And the reason for that is that primarily, microbes can increase mineral dissolution rates through microbial weathering or bioweathering, and they can also facilitate precipitation in their environment through their own metabolic processes. So the two main strategies for targeting accelerated weathering with microbes are field-based techniques, using microbes on croplands, forests, and all those other potential areas where we can spread our tailings, or even incorporating them into tailings ponds, which exist on mine sites. Or we can use microbes in a more reactor-based system, which offers a more controlled setting, optimized conditions, easier to know what's going in and measure what's going in and measure what's coming out. And there are a number of active projects out there on field-based systems, but we in Details plan to take a more reactor-based approach. We know that certain microbes can and do thrive on mine sites, and these are just the examples that were documented when we visited the PGM site in South Africa. They also thrive within wastewater treatment works, which are used on site or in other industries. But as you can see in these photos, they live, they exist, they thrive in tailings, in processing waters, in the concentrator plants, basically everywhere. And that's obviously important because if we're to use microbes, we need to know that they can survive in such environments. And what we want to do with microbes and what we're targeting is using specific microbes which can facilitate a two-stage pH switch. So let's envisage two different bioreactors. The first one, the microbes act to increase mineral dissolution rates by bioweathering, and in the second reactor, initiate precipitation of carbonates or microbial-induced carbonation. And what we're going to explore is these opportunities with the nitrogen cycle, where microbes create this pH switch in the first reactor, creating a low pH through nitrification. That's our weathering step. And then in our second reaction, creating a high pH coupled with the production of organic molecules and nucleation sites, which encourage carbonate precipitation. And that's through denitrification and nitrate reduction to ammonium. So this is the first stage of that weathering step. Microbes can influence or even control weathering of minerals in various ways, either because it's just beneficial to them. For instance, the bacteria link to the elements to be used by the cells, or by indirectly producing organic compounds. That can lead to the mobilization of mineral-bound metal cations, so our magnesium and calcium is mobilized, and by acidolysis, from the release of these organic acids into their surroundings, which again can break down minerals containing our magnesium and our calcium. To put it simply, they can create more acidic conditions that can lead to increased weathering rates and increased dissolution of silicate minerals. These reactions and conditions are created by redox reactions that microbes perform to conserve or create energy for themselves. Similarly, in the second step, where we want to precipitate our carbonates or induce carbonation by microbial means, this can, again, either be done directly or indirectly. So microbes can actively precipitate carbonate inside their cells. They can also indirectly modify the surrounding environment, leading to the precipitation of carbonate owing to hydroxide release. They can provide nucleation sites, which are essential to precipitate our carbonate minerals. And they can produce carbonic anhydrase, which is a catalyst for the conversion of CO2 into carbonate ions. In other words, they can facilitate the ionic form of CO2 that can then be precipitated when bound to our cations, such as magnesium and calcium, which were produced and released in our previous step. So that's all about the nitrogen cycle. Just for a comparison, it's useful to point out some of the results from a similar cycle, the Sulfur Cycle, which we did work on in the G Group project. So the inherent benefits of using a sulfur cycle-based microbial approach are low resource usage to grow these particular bacteria, limiting the use of energy and water. These microbes have an inherent ability to fix carbon, and they create the same pH switch, just like with our nitrogen cycle. So that facilitates our acceleration. They're also slow growing, which makes it easier to control and monitor them. So the experiments that took place did so under ambient conditions, which again is another benefit. We didn't need to pump or sparge CO2 at this point. Any CO2 that we did pump could increase reaction rates. And these, what we'll call sulfur-loving microbes, grew over a couple of weeks in the presence of tailings, and in some cases even thrived in the presence of tailings. So we know again that these things can survive in the presence of tailings. And whilst growing, the bacteria lowered the pH of the solution to approximately pH 2.5, creating an acidic environment, and that coincided with microbial cell division. So acidic conditions were created and then buffered by the microbes. We saw that the microorganisms were initially inhibited in their growth, but they eventually overcame that. And eventually, we also see cation release, so magnesium and calcium release from the tailings, coinciding with this microbial growth and this pH drop, suggesting that all these processes are linked and this process actually does work. We saw it for magnesium, calcium, and also silica ions. They were all released, something that we see with our microbes, but we didn't see in our control samples. So when we had a sample next to that didn't contain the microbes, we didn't see that same release of concentration of cations. And what's good about that sulfur cycle, or the one that we want to test in details, this N cycle, nitrogen cycling, is that this two-stage system, the product of one reactor is the substrate for the other reactor, and that works vice versa. So we might even have a self-sustaining system on our hands, something that needs to be explored. Here we have the basic design of the two interconnected bioreactors to speed up the weathering and carbonation processes by this pH switch. In the weathering reactor, nitrification converts ammonium to nitrate with an accompanying pH decrease and subsequent release of cations that produce alkalinity. And in the precipitation reactor, nitrate reduction to ammonium creates pH increase. We create nucleation sites, and this all aids carbonate precipitation. And then the products from that weathering reactor are fed into the other reactor as well. And the cycle goes on. So we're hoping to eventually test and upscale this design to kilogram materials or even bigger. And just to start summing up now, ultimately, we're looking to work with a range of samples, perhaps some more promising than others, at a lab scale, and eventually at an upscaled bioreactor system scale. And ideally, this will fit within a mine processing or a wastewater treatment style plant for easy integration into the waste tailings management system. And just to divert briefly, a quick note which should be of interest to people in this audience in particular. It is possible that Spain has the potential to be a European leader in geochemical CO2 removal approaches. As we probably all know, there are several highly appropriate rock types in all corners of mainland Spain, including here in Catalonia, and also across the islands as well, especially the Canary Islands, which are essentially a lot of it is basaltic or gabbroic peridotite, all the materials that are promising for CO2 removal strategies. We can also use limestone. I don't have time to go into how we can use limestone. It's a process called ocean liming, but this is another CO2 removal strategy which could be implemented. And similarly, desalination reject brines are also a source of magnesium and calcium, and electrochemical winning processes are a method of removing CO2 through these materials. And there's large industries in Spain that could be catered to CO2 removal approaches. We also have the hot climate, especially on the Mediterranean coast. We have kilometers worth of greenhouses, agricultural fields, vineyards, coastal lands. We have the steel making industry. There's a lot of viable options that could be used for enhanced weathering. And this is something that's been a bit of a curiosity of me for the last week or two. So this is very fresh and new in my mind, but it's something that we're hoping to put something together, and it's definitely worth investigating. So to conclude our work so far on the details project and where we hope to go, we see the high potential in volumetrically abundant mine tailings, particularly certain types of tailings that have the right ingredients, magnesium and calcium, to react with CO2. But there is still a need to speed up our weathering, our mineral dissolution, and our precipitation rates. And our microbial approach seems to show a lot of promise there, which is something that bodes well for the mining industry, as these things do thrive on sites and in wastewater treatment works. And we hope to make some good progress over the next couple of years towards a viable, upscaled pilot scheme. And as industry interest ramps up, as academic interest ramps up, as people like Elon Musk start throwing money into these things and other big funders, we hope that we'll come to possibly an integrated scheme that goes beyond enhanced weathering, that includes direct air capture and other methods of CO2 removal and CO2 reduction strategies, so we can start to achieve that gigaton scale removal that we need according to all the reports. And hopefully details will be a big part of that. And so that's a very quick overview and skim through the project. Thank you very much for your time today.